Hi, welcome to lesson 16 in the use of JASP in understanding statistics. Today we're continuing to talk about reliability. It's lesson 2. I want you to go into JASP, go to open a file, go down to the data library, and let's go down and pick a data set from the reliability module. We're going to go with ADHD symptoms. And I'm not going to pay attention to the analysis that they have here for standard error of measurement. But I do want you to take note of the nature of this sample. There's a little over 1,000 children whose parents rated them on symptoms such as my child has difficulty keeping attention on task or play. And each one of these items that the parents rated were rated on items going from 0, a judgment of approximately never, to 4, very often. Is like a Likert scale, although technically not a Likert scale. It is a ordinal measurement system. Okay, let's go ahead and take a look at reliability. We're going to go to unidimensional reliability. Take all the items. These are the symptoms. Plug them in over here, and we come up with a coefficient omega, or McDonald's omega, of 0.884. It's nearing giving us a excellent reliability score. Under analysis, I can go ahead and compare that with coefficient alpha, which is very similar, 0.882. You can look at the split half coefficient, and that is 0.872. So all of those are in alignment. So we have good reliability. Let's see why we have good reliability. Go ahead and click on item rest correlation. Item rest correlation tells us the correlation of each symptom with the average of the rest of the scale. So it's showing that symptom 1 correlates about 0.64 with the rest of the scale. Symptom 2, 0.71. Symptom 3, 0.49. Notice that all of these are strong correlations. They're in the range of 0.5 to 0.7, and that demarks a very good scale. If we look at coefficient omega, if the item is dropped, notice that we're starting off with a coefficient omega of 0.884. So do we get anything larger if we drop an item? 0.871? No, that's lower. 0.865? No, lower. 0.882? No, 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 no. All the way down. All of these estimates are slightly lower, indicating that if you were to drop out an item, like if I were to drop out item 1, it's saying that my reliability would change to 0.871, which is lower than there. Let's test that. And there you go. It's actually correct. It did drop to 0.871. So all of these items are valuable. Let's take a look at our advanced options. The idea of coefficient omega is that there is a unidimensional scale that underlies that measurement system. And here you notice that if you go to the advanced options, it actually says it'll give you an option for a single factor model fit. So is there a single factor that underlies that? And here it gives you some results that take a lot of learning to figure out what that means. But it's given you, most importantly, just to start you off, with an index called the RMSEA. And the RMSEA, if it's around 0.08 or lower, I prefer it to be 0.05 or even lower than that, but 0.08 and lower is pretty much an acceptable fit. So this is showing that we have a generally acceptable fit for the single factor model. If you go to PFA and then standardize loadings, It's showing you the factor analysis loadings that you would get, and they're all healthy. What's a healthy factor analysis loading? The factor analysis loading is the correlation of the item with the factor, the latent variable. And you want each of those to be ideally strong. So that means zero point 0.5 and above, and all of those are strong. All of this indicates that we have a single factor and its reliability is good. But let's push ourselves a little bit and let's look at this via factor analysis. This giving you a very, very cursory view of factor analysis here, and we'll delve into it more deeply later on. If we go to exploratory factor analysis, I'm going to take these items and put them over here. And it's giving me the factor loadings as I saw them before. I'm going to go to analysis options and output options. And under output options, I'm going to go ahead and click on a path diagram and a scree plot. This path diagram is representing the idea that there is one factor that underlies the symptoms. Now, what does that mean? And why is it that the arrows go from this circle over to the items? The circle represents the idea that ADHD is a latent construct. Let's give it a name that basically makes more sense. So ADHD usually has two components, inattention and hyperactivity. Those two can combine, but let's assume that these symptoms are inattention symptoms. That fits with the first item. So imagine that you have this construct called inattention. You can't see inattention. You can only see symptoms of inattention. And the idea here is that the inattention of the child results in behaviors, causes behaviors that the parents then give reports on. So each one of these arrows represent going out from the inattention construct to the symptom. And this is called a common cause model. It's the idea that all of these symptoms are due to this one common cause. And this model is fundamental to McDonald's omega, or coefficient omega. So there is an example of a measure with good reliability, and I don't want to load you up with too much. We need a number of examples of factor analysis and a deeper dive into factor analysis to understand how reliability and factor analysis connect, how to choose various factor models and what various factor models might look like. But here is a quick example, and I'm going to go ahead and stop there.